Hello and welcome back. Let's see. Today we're going to do something a little bit different. Last night I discovered this series of puzzles called D&D Sci, and my understanding is that these are basically like fantasy themed data science puzzles. Now, disclaimer: I am by no means a data scientist. I forgot most of everything in every statistics class I've ever taken, but APL, which we're going to be using today, specifically dialogue, is, I believe, a pretty good tool for kind of data exploration and sort of, manipulating it to gain different insights. So while I am a rank amateur at this, let's see how far we can get with APL. So there's a bunch of different scenarios in here, and depending on how this goes, I might do more of these. But I figure, there's this one towards the top with the highest quality rating and middle of the road difficulty. So this is called Archmage Anachronos and the Supply Chain Issues. Blah, 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 much like Advent of Code, there's a bunch of flavor text here, but we'll skip most of it. So the nuts and bolts of this is that, so we get some data which appears to be a CSV file with mostly Boolean numeric values and some text. Our Archmage here is trying to brew a barkskin potion. Okay? And there's a bunch of ingredients that he can use for this, some of which he has none of. So we can't use any of these ingredients to brew our barkskin potion, but he does have access to these, so we can use any of these. Our goal is to figure out which of these ingredients he should use to maximize the odds of brewing a barkskin potion. And we can use any number of different ingredients in a potion, but cannot use any ingredient more than once. So basically, given all of these ingredients, we have to identify some subset of them that maximizes our chances of brewing a barkskin potion. And the CSV contains a bunch of past potions he's attempted to brew, lists which ingredients he included and what the result was. And results are either successfully brewing some potion or another, or something went wrong, right? The general way that I think these go is like so they post these like rule set discussions, which I haven't looked at any of them because I want to avoid spoiling myself, but I think like they generate the input using some rule set, and then basically if we can figure out the rule set, then it becomes pretty easy to solve the problem. In this case, successfully brewing a barkskin potion, right? So CSV file, do a bunch of data analysis, brew a potion. Sounds good. Let's try APL. So hopefully this font is okay. Now, I've never used this, or maybe I've used it once or twice, but Dialog has this quad CSV function that's pretty useful for pulling in CSV files. So we have D&D, what's it called? D&D Sci hotdata.txt, I think it is. And I believe this is quite large. I guess we're about to find out. So I'm going to be very careful to try and not type any expressions in here, which print millions of rows to the interpreter and hang things. How big? Okay, so we have 118,000 rows. And if we just look at the first two rows, yeah, so looks like the first row here is going to be our CSV headers. And we have some ingredient names, a bunch of ingredient names. We have some result column, and then on the very end, we have a success column. Okay, fair. enough. Okay, so let's see. One thing that seems reasonable to do is to take the first row of our input here, and then we can drop the first or the last two elements, right? And this will just give us a list of our ingredients, which I suppose we can call I. And let's, just so we don't get lost, D&D pots.dialog. Yeah, sure. Let's just copy some stuff here so that we know what we're doing. So we pulled in our CSV file, and then we identified some ingredients. Man, I have no idea. I have no idea how this is going to go. I don't know if this is too hard for me or not. I've not done that much data science stuff, but I guess we'll find out. Okay, so we have ingredients. I guess we can pull out the latter two columns, the success and result. So if we do like one drop P, and then let's say we take the rightmost column, and the rightmost column is what? Boolean values. So we'll do for each execute the other one. And I guess we'll call this like the success column for SC here. And if I take like the first 10 elements of SC, this looks fine. Wow, yep. So, and we have, okay, so there's 72,000 successes versus, where's my tilde? There we go. Versus 45,000 unsuccessful things. Okay, let's take the result column out as well. So that's also going to be one drop P. And then we can do, how do we want to do this? Can I do negative indexing? So -2 index rank 1. So for each one of the rows. And then let's take the unique, well, yeah, let's take the unique values. Let's see what this gives us. Index error. -2. Oh, oh, I guess I can't do. No, I should be able to, right? Sorry, I'm a little bit rusty. I haven't done that much APL recently. No, I guess I can't do negative indexing here. That's unfortunate, but I bet I can do. You can do something like iota 10, and you can use the index operator, right? No, that doesn't work either. Okay. So, tell you what, how long is ingredients? Length ingredients, 24. So it's going to be at index 25. So let's just do this. Yeah, okay, perfect. Okay, so these are all the unique results that we can get. Magical explosion, potions, inert glop, potions, acidic slurry, mutagenic ooze. There's our bark skin potion right in there. Okay, cool. So let's call this like R for results, right? And then for the result column, we can, instead of doing unique here, we can take results and index into that so that we're storing indices rather than a bunch of strings. And we'll call that like the results column, right? So if I do 10 take result column and I use that to index into results, I should get a bunch of results. Yeah, okay. Okay, so this all seems good. Let's copy our stuff here. So we have the result columns, we have results and result columns, and we also pulled out our success column somewhere here. Okay, cool. I mean, you know, making progress, just parsing the data set, I guess. Well, one interesting question, I guess, is what the wizard actually considers successes or not. So we can do like, we can use the key operator on the success column, and then we could do alpha. How do we want to do this? Alpha, and then there's going to be. Oh, I know. We take the result column, index into W, and then we index that into R, and then we enclose it, right? So we take the indices that key finds from the success column when it's doing the grouping, transform those into result indices via RC, and then we look at the results. Okay, nope, that might have. Hold up. Success column. What are the unique values in the success column? 0 and 1, right? So there shouldn't be. Oh, I should hold up. I should do RC. I should do unique here, right? Instead of, there we go. Instead of printing out literally all of the results. Okay, yeah. So the wizard, a 0 means these 4 kind of failure modes, I guess. Magical explosion, inert glop, acidic slurry, mutagenic ooze. And then a success means one of the many types of potions that this guy has tried to brew, right? Okay, cool. Now, as for so if we look at P, or at least the first 2 columns, so each one of these ingredients, if there's a 1 in that column, it means that it was included in that attempt, and if there's a 0, it was not. So let's just render this thing as a big ol' Boolean matrix. So we'll do 1 drop P, and then we'll do -2 drop. I can use negative indexing here, I'm pretty sure. I can get the character right. Yeah. And this we can do rank 1, and then for each one of those, execute it, and we'll call this like T for table, I guess. That takes a minute, but then like let's take the first 10 rows of T. Yeah, it's a big old Boolean matrix. And this is, by the way, Boolean matrices are like APL's bread and butter. So if we look at the size of T, or the amount of space that it takes in memory, that's 355 kilobytes. And if we look instead at sort of the string representations of everything, or the sort of raw data that we pulled out of the CSV, that is what, nearly 150 megabytes. So yeah, I mean, it's storing the 0s and 1s as character strings, but still. So all this is one contiguous region of memory, and all the analysis should be fairly fast. I don't think, even with 118,000 rows here, like having done some fairly large advent of code problems, I don't think this is going to pose a problem for us. Okay, so we define our table, right? So T is this table. Okay, cool. What are some fairly basic questions that we want to ask about the data set? I guess, so we already figured out, like somewhere in here, we were looking at the number of successes and failures. So there are quite a few more successes than failures. I guess that's good to know. What about how many ingredients are actually included in each one of the different attempts? So let's do sum scan, or sum reduce on the rows. And then let's, first of all, just like, what's the minimum and the maximum amount of ingredients included in all attempts? So it looks like the minimum number of ingredients in every attempt is 3, so we'll never have 2 or 1. And then the maximum is 8. Okay, that's good to know. What about, you know what would be useful? I think probably we want to do like a bunch of kind of partitioned analysis on the different result types. So what if we what if we had like a nested vector with all of the with like a bunch of Boolean matrices that only relate to a certain result type? What's a good way to do this? So we could do like iota length result, and then we can do like an outer product. Um, we can do an outer product with the result column, right? Let me think about this. Yeah, okay, yes, I think that works. So, and then this will generate like a pretty large matrix. So 14 rows, each one of the results plus the entirety of the table. And then we can split that. And then for each one of those, we can use, for each one of those, we can use it to filter the table. And you want to do filter first to filter along the rows. And this might actually do it. What do we want to call this? Just like, let's call it like RPT for like result partition table, I guess. And then for each one of these, what is the shape? Okay, yeah. Yeah. So this partitions, basically we have like a bunch of Boolean matrices in here, and each one of the rows is particular to a particular result type. So we were talking about like the amount of ingredients here, and it would be cool to know like the average number of ingredients, I guess, for each result. So for each result partition, we can do, this will be, like this. And then we want to find the average, which is divided by length. So we sum along all the rows to get the number of potion ingredients in each row. And then we sum all of them together divided by the length of that list to get the average. Right? And hopefully, okay, yeah, this is just a vector with 14 elements. I'm being very careful not to flood the output here. And then we can kind of just prepend. Hang on. Okay, a little rusty like I told you, but we'll get there. Okay, interesting. So these are the average number of ingredients for each one of the different results. Let's hold up. Yeah, let's do this the other way around, and then let's sort this descending. I think I have to put a semicolon there to sort along the rows. Okay. So mutagenic ooze has the most ingredients, followed by magical explosion. These are both failure modes. So maybe they have something to do with like having too many ingredients, but it's like super close to what we actually want to do, which is the barkskin potion. So maybe be careful of that. And then let's see. Acidic slurry and inert glop are at the bottom. So maybe these are about not having enough ingredients in some way. That is interesting, actually. Okay, let me just take some notes here. For failure modes, right, we have mute ooze, too many ingredients, and then magical explosion is like the same. And then what else do we have? So we have acidic slurry, too few, and inert glop the same. Okay, this is So this is a useful little analysis table here. Let's call this like uh, uh, naming things is hard. Okay, result, average, ingredient counts. Done. Race. Okay, cool. So we'll put this over here. What else would be like useful? Um, how about like the average number of each ingredient for each result? That would be cool. So for each result partition table, let's see. How would I do this? Average number. Okay, so we sum each one of the columns, and then we do. Oh, this is just each one of the columns divided by the length of W, right? Okay, and that's 14, so cool, let's take a look. Okay, yeah, so this is like a bunch of nested stuff. Then we can get a matrix. These are percentages, so we can multiply each one of them by 100. Cool, and so that we know what we're looking at, we can again append results on the left, and then we can do like enclose the empty string on the beginning of our ingredients vector, and we can layer that on top. Okay, cool. Let's pull this out of the way. Yeah, so this is the average. What does this measure? So this is the average, the percentage of the time that each ingredient was used in each one of the results, right? So there are some hundreds in here, which I guess means for like each one of these, there's like each time that that result occurred, that ingredient was used 100% of the time. So if we look at like bark skin potion, yeah, we got 100 there, and we got 100 there. Ground bone. Hang on. Are these like? I don't see any ingredients that are used 100% of the time in multiple potions. I don't think. I guess we can check that. Sorry, I'm scrolling all over the place here. So if we get rid of this kind of formatting garbage and we just look at the data, we can do maximum reduce along the columns, and we get this. But I don't want max. Hang on. What do I want? I want to know if 100 was used multiple times. So we'll do 100 equals, and then we do this. Okay, yeah. Yeah, so like some ingredients are not used 100% of the time at all. But then for all the others, they're used 100% of the time exactly once. So there's like either an ingredient is not required 100% of the time for certain things. There's 4 of these, so maybe these are our failure modes. But then like each other ingredient is uniquely associated with some potion. Let me think about this. What's a good way to view this data better? So we have our big matrix of percentages. And then let's say that we break that down. And then for each one of those, we can do like, I want to sort, yeah, I want the biggest ones first. So sort W, assign that to like X, it's just a temporary variable. Index into W with this. And then also let's put the, let's index into ingredients using the permutation vector, the sort vector, and we'll layer that on the left, and then if we transpose it, we should get a horizontal arrangement. Yeah. Okay, cool. And then, so we can do the old slap our results on the left trick. And okay, so this shows, this is the same data, but now it's like for each result, what's the most used ingredient. And yeah, so we can see for the failure modes, there's nothing in there. Hang on, by the way, is there, before I look at this further, if we go back to our percentage data here, is there anything, like what's the global minimum of this? Is there any ingredient that's never used? Or like, yeah, is never used in a particular combination? Okay, so the minimum out of all these percentages is 6.25. So basically for any outcome, potion or failure, an ingredient was used in some attempt at least once. So there's no ingredient that like precludes a certain result simply by including one, simply by including it by itself, right? Anyway, so okay, and then for each one of the potions, there are ingredients that are used 100% of the time. We can call these, I don't know, call them like required ingredients or something, right? Like, so if we're trying to brew a barkskin potion, I definitely want to include crushed onyx and ground bone, right? I don't know if like the rule set that he's using actually requires these, but you know, our data says that it would be a really good idea to include those. And then we also know from the analysis on the percentages that each one of these, like basically each one of these 100% ingredients is unique. So like crushed onyx is a required ingredient for barkskin potion, but it is not a required ingredient for anything else. And same with ground bone, right? Now the failure modes, so we want to successfully brew a potion, and presumably we want to avoid these failure modes. So let's see. Where's my horizontal scroll bar? Okay, thanks, macOS. Vampire Fang. So probably don't want to use, actually for like the most common ingredient for any one of these, maybe we just don't want to use that. Right? But like, so even in terms of most common ingredients for failure modes, Vampire Fang is pretty high up there. So for like inert glop, ground bone, you get it 31% of the time. Acidic slurry, fairy tears, you get it 30% of the time. Oh, well, oaken twigs is also 40%. So let's see. Vampire Fang, Giant's Toe. These percentages they drop off pretty slowly. And then once you, oh, this is all dragon stuff in an order. I think this is all the dragon ingredients, maybe, or are there other ones? But they're all in order there, which is kind of interesting. And then, yeah. And then it drops off some more. And then at the very end, you get crushed sapphire. What can we infer about any of this data? Okay, well, anyway. Inert glop, ground bone, oaken twigs. These all also fall off fairly slowly. Badger skull, quicksilver, ectoplasm, troll. Wait, dragon tongue. Here's all the, well, here's 3 of the 4 dragon things again. on the other ends, and then an angel feather. So, like, hang on a sec. This is all, hold up. Vampire Fang, Giant's Toe, Troll Blood, blah, blah, blah. Demon Claw, Dragon Spleen, Angel Feather, Beholder Eye. Okay. And then you get Powdered Silver, Redwood Sap, Beech Bark, Badger Skull. These are all like, these are all things that actually exist. I mean, Eye of Newts is the kind of stereotypical like witch's potion ingredient, but it is, I mean, there are newts and they have eyes. Crushed gemstones, those all exist. Those are like real things. But then like dragons, angels, fairies, I mean, this might be controversial to say, but these are all basically things that don't exist in real life, right? Like Vampire Fang, Giant's Toe, Troll Blood. But then the weird thing is for Inert Glop, it's the other way around, right? So like Eye of Newt, Redwood Sap, Badger Skull, Crushed Gemstones, those all exist. But then you get to this point with Ectoplasm. And if we go down the row here, more dragon stuff. Yeah, those are all things that don't exist, right? So what if magical explosion is caused by including like too many I don't know, let's call these fantasy ingredients, and then Inert Glop is too many real ingredients, or maybe like too few fantasy ingredients. I guess that's maybe another way of saying the same thing. Okay, well, okay, so let's hang on to that. And then we have Acidic Slurry, which the grouping is more tight here, I think. Actually, you know what would be cool? Hang on. I think that there's like, so if I just look at the raw, so if I do this and then, oh no, it would be, so if I look at the table and I take like the first item, right? And then we can, geez Louise, we can take the rightmost column, we can break that out, and we can take the bottom column, I guess. Yeah. There's like, I fooled around with this once, but there's like a plot library, I think. I'm not sure if this got added in Dialogue 19, but hey, it appears to work. So we get charts now. Wow, that's cool. We're real data scientists. So yeah, 40 to 16, and the drop off appears to be like fairly linear. And that's for magical explosions, right? So if we take our index of, what was the other one where the distribution looked tighter, for lack of a better word? Acidic Slurry. So if we take the index of Acidic Slurry, yeah, we'll close it, in our results, and then we do this same thing, but instead of the first index, we take the fifth index. Oh, does this just, it keeps the window open, but it updates it? Yeah, the distribution for this, yeah, it doesn't go all the way up to 40, but then you get this like weird drop off around the 21st ingredients. So where was that table? Where is Acidic Slurry? It was here. Fairy Tears, Ectoplasm, bunch of fantasy items here. Oh, a Quicksilver. Yeah, okay. So these are kind of mixed. Well, there's a bunch of fantasy items in the beginning. Beach Bark. Where was that weird drop off? Yeah, here. So there's like a drop off between Redwood Sap and Crushed Onyx that looked a little interesting. I don't know what to make of that at the moment. There's a fourth failure mode, mutagenic ooze. So, what's the index of mutagenic ooze? It is, yeah. Enclose, it's 8. So let's look at the plot of that. There's a little bit of a curve to it, huh? But this looks more like the distribution of the um, what was the first one? The magical explosion. So not much that we can infer about mutagenic ooze from the distribution. Oaken twigs. So this is the other way around. Whereas with acidic slurry, it was mostly magic items in the beginning. This is mostly um, real items, although Vampire Fang shows up. And then, yeah, I can't really tell you. I can't really tell you anything about these percentages. What about our target? What about Barkskin Potion? So we know we have 2 required ingredients: crushed onyx, ground bone. 2 ingredients down, probably some more to go. Troll bloods. Like maybe we just throw the most common ones in there, but there's also like, let's not forget that our employer, Mr. Mage, has access to some ingredients but not others. So like a naive thing to do would just to be throw in some like X number of additional likely ingredients and call it good. But yeah. This is yeah, I can't tell anything about this distribution either. Okay, whatever. Anyway, so we found out one thing to follow up on. So this is an idea, okay? What if all this stuff, the fantasy items, like appears in Magical Explosion, and then all the real items appear in Inert Glop, right? So let's see. Oh, have we saved our little analysis table here? Uh, Man, what did I call this? This is the downside of short variable names. Result something ingredient count. Result average ingredient count, right? Well, anyway, I got it. Oh, but this is not the sorted version. So let's save that. It is this one. So this is, listen, naming's hard, as I keep saying. Result sorted average ingredient count. Wow, I'm a poet. Okay, cool. So first of all, let's figure out what the fantasy ingredients are. So we'll do like iota length ingredients and then tack ingredients on the left of it. And okay, we'll write this over here. It's probably easier. So we're going to have a list of like fantasy ingredients denoted by indices. Angel Feather, that's one. Beholder Eye, throw it in there. Demon Claw, Dragon Scale, Dragon Spleen. Dragon's Tongue, Dragon's Blood, Ectoplasm. Fairy Tears, Giant's Toe, and all this stuff exists. Troll Blood doesn't, and Vampire Fangs hopefully don't exist. Okay, cool. And then, so this will be our fantasy indices, and then our like real indices will just be iota length I without our fantasy indices, right? Cool. Fantasy indices, real indices. What do I want to do with these? So we can do a kind of partition table the same way, where let's say, so we do fantasy index. Wait, hold up. No, I want to do iota length. Let's do iota length ingredients membership in fantasy indices. This gives us a Boolean vector. And then we could separate these with key, and then we would take our result partition table, index there, and we would want to concatenate all those, break it out. Wait, is that right? No, we don't even have to do that. Ooh, this is going to be... No, I don't want to mess around with the result partition table. So let's go back to T. And what's the way to do this? Oh, I got it. Okay, so we have our... oh, let me think. So if we take T and we get... actually, you know what I want? No, this is already a Boolean vector for... Yeah. Hold on. So I could do like an and then an or reduce. And then we could key based off of that. We could key based off of how many magical ingredients. Okay, so let's do, let's take table and then rank 1. We'll do like and this thing. And then we'll do plus slash to see how many magical ingredients was in each row. And then we can key off of that, and we will do the result column index W, unique results index, and then we'll put we'll put alpha there, but enclose this. Okay, did I mess up? What's the shape? Function requires a left argument. Yeah, what was I thinking? This should be over here. 8.2, okay. Okay, neat. Let's sort this. W, just the rows. Okay. Okay, yeah, interesting. So, all right, I realized that was mostly I was just mumbling to myself, but like, so this data, basically the left column is the number of fantasy ingredients that were included in some subset of our data. And then the right column contains a unique list of all the results that were found for that number of fantasy ingredients. And we can see that like, so 7, 6, and 5, 7, 6, and 5, you get a magical explosion. So basically, we don't ever want 5 or more fantasy ingredients. And then on the flip side, if you have 0 or 1 fantasy ingredients, you get inert glop. So we want 2 or more. And we probably want to be like in the middle here. Yeah, you can still get a magical explosion on 4, but it doesn't happen all the time. And you can still get inert glop on 2. I wonder if there's some way where I can get the percentages here. So let's see. So rather than taking unique here, man, what's a good way to do this? So we index into RC. Okay, let's start over with this function. So we index it into RC, and then we could do a nested key. And then for each one of those, the idea would be, and let's assign W to some temp variable X. And then this would be like, so it would be length W divided by length X, right? And then we probably want to, let's do, so we can, hang on. So we can put our results there, but we'll put it on the right side, and then we can sort the resulting matrix, just the rows, right? And that's a big nested key. And then we'll enclose this and then alpha. Right? Oh, this probably, no, I don't have to enclose that one. Okay, let's try it. Hopefully the terminal doesn't blow up. Here we go. Length error. Oh yeah, no, we do, you don't want to put the result here. You want to enclose this and then index into results here, right? Probably. Index error. Result columns. Oh yeah, no, this is not W, this is alpha. Oh, hey. Oh, and then these are percentages. So let's do 100 times here. Okay, cool. Yeah. So with 0, 1 fantasy ingredients, you get inert glop 100% of the time. Wait, no, this is different. Is it? Oh, no, you're supposed to, oh no. Yeah, hang on. This is sorted by, this is sorted the other way around. So let's just put this on the other side so that the sort takes into account the percentage first. Okay, yeah. Okay, so if you, so 0 or 1, you get inert glop 100% of the time. If you include 2, you get inert glop around 50% of the time, let's say. With 3, you get no failure modes whatsoever. Oh no, you do still sometimes get mutagenic ooze or acidic slurry. But maybe like the criteria for these is different, right? So it seems like inert glop and magical explosion are sort of measuring this criteria. And then these other two have their own criteria, which we have yet to figure out. Okay. But like, you never get a magical explosion or inert glop if you have 3 fantasy ingredients. And then 4, you get a magical explosion say 50% of the time, and then 5 and up, you get it 100% of the time. So let's just add to our notes here. So magical explosion, let's say 4 plus FIs. And then inert glop is 2 or fewer FIs, right? And these, oh wait, no, that was actually a valid. So maybe like, yeah. Okay, so we now know how to avoid these failure modes. So we have 2 ingredients that we know that we need for bark skin potion, and then we want to make sure that we also include 3 fantasy items, right? The only other thing is that we want to avoid these 2 failure modes, which the only clues that we have right now is mutagenic ooze had like a bunch of ingredients. It seemed like very high average number of ingredients, and then acidic slurry had a pretty low number of ingredients. So okay, yeah, that's cool. All right, cool. So I wonder if, hang on, let me look at this table again. Oh, let's also insert this monstrosity. So this is our, geez, Louise. This is like fantasy ingredient count results. There you go. Okay, cool. So the only clues that we have to go on were this thing. So we're looking at RAIC, was it? Result average ingredient count. Yeah, mutagenic ooze is the most. Inert glop is. I guess this makes sense, right? Because if this is based on how many fantasy ingredients that you contain, it makes sense that it would have some sort of correlation with like low numbers of ingredients in general. But then acidic slurry is the very next one up, and it's quite close. So there could be, maybe there's some other category of item that, but looking at the percentages, I didn't, that was, the fantasy item thing was the only one that stood out to me. Okay, well, so far we've only really looked at, let me think. So far we've only looked at kind of individual ingredient counts. So if we look at results, average ingredient included, not this one. Oh, I didn't copy my percentages here. What was RSIC? Oh, I didn't even define that one. Okay, hello? RSIC? Yeah. So we're looking at a bunch of these percentages and stuff, and this is all cool and whatnot, but this is only looking at individual ingredients, right? What if acidic slurry or mutagenic ooze, like let's say there's an ingredient that you include where normally it's fine, but you include some other ingredient and all of a sudden you get some sort of failure mode, right? And I guess this could extend, like there could be triplets or quadruplets of ingredients that cause failure modes, but well, if that's the case, then looking at pairs of ingredients would help point the way to that, because certain pairs would be more likely than others to result in failure. So what if we do the same kind of percentage analysis here, but rather than looking at individual ingredients, we look at pairs of ingredients? How do I want to do that? So like, I could do, it would be cool to have a Boolean matrix for all possible pairs. And what's the way, so I can do like, I do iota length ingredients, I can get an identity matrix like so. So each row specifies the inclusion of one ingredient. And then I guess I can do another outer product here where, so for each one of these, we just do OR, right? So it ORs them together. And then let's do, I'm not going to print this out to the console because it's going to get pretty large, I guess. We'll turn those into a vector and mix it. This won't be so large that it breaks the console, I guess. What's the shape of this? Oh, yeah. 576 rows by 24. But some of these are non-unique, I would guess. Yeah, so that gets us down to 300. And then we only want the ones that contain two distinct ingredients. So we can assign this to our good buddy X, the temporary variable. Sum the rows, 2 equals, and then use that to filter X. And yeah. Okay, so that gets us down to 276 rows. And if I just take like the first 30 rows of this, yeah, this looks right. So this is, so for the first ingredient, this is all the possible combinations with all the other ingredients. And then we skip over to the second ingredient. So this is kind of like permutations in a way, I guess. This is just like a pretty, honestly, pretty inefficient, like outer product-y way of doing it, but whatever, it works. Okay, and then, so let's call this like AP for all pairs, right? So these are all possible pairs. And then we probably want to, how long is this? AP? So I guess we take, geez, how will we do this? So that's all possible pairs, and then we want to segment it based on results, right? Oof. So I guess we need an outer product, index length R, outer product, some function with all pairs, the split of all pairs. And this would be alpha and rank 1 with W, right? And then we can sum those. And if it equals 2, meaning that both the ingredients were there, then we can use it to filter. No. Hang on. Sorry, I'm thinking. Result partition table, actually. We want the rows, so let's do result partition table over here. And then, yeah, this will be each one of those partition Boolean matrices like this. And then we can use this to filter alpha. Right. And this tells us how many. Actually, we can just sum this. And then, hang on. What's the shape? 14, 276. Yeah, whatever. I can support 276. Okay, cool. So this is, zeros. This is the amount of times each pair was used in each one of the different results. So 14 rows, each one for a different result, and then 276 columns. And I do see zeros in here. What is, so if I vectorize this and I take the minimum and then the old minimum maximum trick. Okay, so zeros, yep, and then 7851. That doesn't really tell me that much. So I am curious about the zeros though. So let's save this table. Let's call it like result all pairs count, I guess. And then we want to do 0 equals result all pairs count. That gives us a Boolean matrix. And then what's the way to do this? So we split these, and then for each one, we get the indices, right? And then we can index into all pairs, just the rows, and then we can index into all pairs, get the rows. And then for each one of those, oh, there's only 2 here though. There's guaranteed to only be 2, so we can actually just do where rank 1. Yep, and then this, I believe, we can just index into with ingredients. And then we'll tack our results on the left. Okay, interesting. So for glibness potion, the pair dragon spleen, dragon's blood never occurs. For fire breathing potion, these pairs never occur. Acidic slurry, one of our failure modes, these pairs never occur. And then regeneration potion, who cares? Inert clop, magical explosion. I think we figured those out. But acidic slurry is interesting. So, these pairs, crushed onyx and ground bone was, if I remember correctly, the required pair for the bark skin potion, right? What was the how do I just get the, hang on, can we do a similar trick to just pull out the, so we had our percentage table somewhere here. Okay. Let's just look at this. And these are the percentages for each ingredient, right? Yeah, 14 for each ingredient, for each result. 1 equals, and then there should only be 2, right? Same deal. So we do where rank 1. And then we can index into, well, the zeros are a problem. Can I remove, hang on, can I remove, does without work, is that a higher ranked thing? Can I just remove 0, 0? Apparently not. Okay, so we'll, APL is kind of frustrating sometimes with what it's, give me the down arrow, with what it supports in higher ranked arguments and what it doesn't. So without the enclose of 0, 0 and then mix it again, yeah, that works. No, but then this messes up our, hang on. Okay, so do this, and split it, and then for each one, we'll say W without 0, index into ingredients. Yep, that gives us empty arrays, and then, yeah, we'll tack our results on the end. Okay, yeah. Yeah. So for Barkskin Potion, it's Crushed Onyx and Ground Bone, which was the pair that never gets used in Acidic Slurry. I wonder if those other pairs are the same thing. So how would I do this? Well, that really would be. So yeah, that's split without commute the enclose of 0, 0. And then for each one, I guess we just do like ingredients W, and this gives us a vector, which we probably want to sort. And then my question is, if I look at, where was it? This one, right? The acidic slurry, which is index 1, 2, 3, 4, 5. So we index 5 here, and then we take the rightmost column and break it out and split it, and then also sort that. Right? Does this match our other thing, this thing? It does. That's a perfect one-to-one match. Okay. So basically, like, okay. So these pairs never appear in acidic slurry. And each one of these is a required pair for some potion. So maybe acidic slurry happens if the ingredients that you choose do not include a required pair for any one of the potions. Right? Yeah. I think that makes sense. So acidic slurry, no rec pot eyes. No required potion ingredients. Oh, we said, yeah, so acidic slurry was, what was this called? RAIC? Acidic slurry was towards the bottom of average ingredient count anyway, which makes sense because this would, just like a Nert Glop, which fails if you don't have enough fantasy ingredients, if acidic slurry happens because you don't have required potion ingredients, then it makes sense that like it would correlate with just being a lower ingredient total in general. And then mutagenic ooze has the most average ingredients out of any outcome. So what if okay, so like magic explosion and inert glop are sort of opposite ends of the same spectrum. What if mutagenic ooze, which has if I scroll way up here, mutagenic ooze did not have any pairs that never appear. So basically every pair is represented in the mutagenic ooze outcomes, at least once. So what if mutagenic ooze is just like acidic slurry, or sorry, just like magic explosion inert glop is like the opposite of acidic slurry in some way. Where, okay, so we have like required potion ingredients. If you don't have any of those required pairs, you get acidic slurry. If you have one required pair, you get the potion in question. But then, like, if you have two or more required pairs, maybe you get mutagenic ooze. How would I test this? So we had our, hang on. So we had, let's just take our result partition table, and then for each one, let's do an and reduce, and then we just take the where, right? So these are the indices of all our pairs that are required. Can I filter out? Sometimes this gets a little weird with Zilda. And indeed, how about enclose Zilda? Would that make you happy? It does. Wow. Okay, so this is a vector of all of the indices of ingredients for all of our required pairs. And then what would be neat is if I could put together okay. So we'll do an outer product on this, and we'll say alpha cons W where iota length ingredients is a member. And then vectorize that, mix it, and take only the unique elements. And how big is it? 55 and 24. Okay. Let's look at it. And these should all have, by the way, these should have, oh, one of them has 2. That's weird. Oh, yeah, because outer product will compare some cells with themselves. So instead, let's assign this to our old buddy X. And then we want to sum it. And it should equal 4. And we use this to filter against X. And we already took the unique values there. So what's the shape of this? Yeah. We'll throw a commute operator in there, 45. Okay, so this is our new Boolean matrix. And then if we add it all together and take the unique values, yeah, now we only have 4 elements. Okay, so this is like our, this is like all required pairs. Okay, don't come after me in the comments. So all required pairs, right? And the question is, what outcomes do you get if these are included? So we want to take our result partition table. And we'll do some outer product on the split of all required pairs. And this would be, oh, no, I don't have to do, hold up, I don't have to do this at all. I can just do for each, and then we'll do, how does membership work? Is membership higher ranked? Monadic function in list. Huh. No, I do probably have to do the outer product. Or there's probably a better way, but whatever. This will work. The split of this, and we do alpha and w rank 1, right? And this is pretty similar to what we did with our other table. So we want to add all the rows 4 equals now, and we use that to filter alpha. No, we do that, we use that to filter the results column, which we then take the unique values of and index into with results. And what's the shape of this? Does this actually work? I keep forgetting this commute operator on the... Oh. Oh, no, it's already result partitioned. What am I doing? Wait. It's already a result partition table. So 4 equals... I think I probably just want the count here. Yeah, how about that? Oh no, this is interesting. Let's do 0 equals add the rows, and then let's throw on our result table. Huh. Interesting. So what, hang on, I lost my train of thought. What are we looking at here? So we did 0 equals. So these are the number of times, the number of required pair combinations that never occur in the result sets. And for everything except mutagenic ooze and magical explosion, there's some number of pairs that, there's some number of required pairs that never occur. But for mutagenic ooze, it's 0. So the hypothesis here is that mutagenic ooze happens if you have 2 or more required pairs. How do I validate this? This is the wrong way to go about this, maybe. Let me look at this data. Is count the right way here? Is count the right way? I don't want count. I want and reduce here. I want and reduce. So this says, oh, but that's all zeros. Huh. 4 more, 4 equals. So apparently mutagenic ooze is not, oh, wait. No, 4 less than or equal to. How about that? No, not that either. Huh. Oh, but this doesn't, wait. Let me go back to the counts. So these are the number of times that each pair occurs, or required pair occurs. This row here is the mutagenic ooze. But the data seems to say that, like, unless I'm doing this wrong. I'm a little bit lost in the sauce here. So alpha and rank 1 omega. And then we add all the counts, and if 4 is less than or equal to each count. I wonder, can I just do that? 4 is less than or equal to. Yeah, this gives us the same. Does it give us the same numbers or is it different? Presumably there's like some where they have, required pair triplets or quadruplets or anything, but I'm not sure. Just doing a scan of the data, this all looks the same to me. What's the size of each? So for our result partition tables, what's the length for each one? This would have been a good thing to look at. Like how many times each result occurs. Maybe. Although the results, like theoretically, this is like randomly generated or is generated as some kind of rule set, so there could be biases here, maybe. 4 equals the sum. So we add those together. Wait, did I do this right? For ARPP, 4 less than or equal and reduce? Yeah, that's correct. Right, this should all be. Yeah, so, oh, that's annoying. Okay, so maybe mutagenic ooze isn't the opposite of acidic slurry. Although the thing with like the average ingredient accounts and everything sort of pointed that way. And the fact that here so every required pair occurs at least once in mutagenic ooze. But the converse is not true, where like mutagenic ooze, every instance of mutagenic ooze contains one or more required pair. I'm just double checking here. So sum it's my alarm to go feed the cats. Well, that's interesting. Wait, hang on. Can this even possibly be true? So like, no, that can't be true. Yeah, so you can have like every required pair represented in the data set for mutagenic ooze, but it can still be true that there are like rows in there that don't have required pairs, right? Yeah, that's interesting. Okay, so mutagenic ooze, I'm not sure about. What else can we try? The only thing that we know for sure about mutagenic ooze, well, okay, so we know 2 things for sure. First of all, it's like pretty close to, it's either the first or second in terms of average ingredient accounts. And then if we include a required pair, then we're probably more likely to get this outcome. because like basically every other potion, every other failure mode except for magical explosion, which we kind of know how that works, has some that don't appear. Okay. Well, yeah, okay, so this video is getting fairly long already. Let's put together a guess and see how close we are. So basically, so if we look at the, where's my required pairs thing that I put together? ARPP. Oh, I haven't been defining all this stuff. This is, that's annoying. So ARPP, hang on, let's just look at, was it RSIC? Yeah, okay, cool. So for Barkskin Potion, we need Crushed Onyx and Ground Bone, for sure. So this is our guess, okay? Crushed Onyx, we'll put each one on a row here. We need Ground Bone, and we want fantasy ingredient count to hit 3. Neither of which is Crushed Onyx and Ground Bone. So we want to add 3 fantasy ingredients, I guess. The minimum count of ingredients for every outcome was 3, and then the maximum was 8. I guess just to double check that, for each result partition table, we do a sum of W, and then we'll do the minimum with the maximum, and then we will put our results there. Yeah, where's Barkskin? Yeah, so for Barkskin, we're okay as long as we're between 4 and 8 inclusive. So yeah, so we throw 3 fantasy ingredients on here. Now our buddy, you can go away. Our buddy the mage doesn't have access to some things, so these are not available. But he does have access to, I think these are, let's go ahead just to be on the safe side. Let's kind of, so if we look at our Barkskin Potion sort of sorted success rate or inclusion rate for each ingredient, let's pick fantasy ingredients in order based on what he has. So Troll Blood. Does he have Troll Blood? He does. Cool. Let's throw it in there. Troll Blood. Oh, we probably also want to steer clear of the required pairs thing, which we'll check in a second. Fairy Tears. You do not have that. Vampire Fang? Wait, yeah, it's this column. Demon Claw. You got a Demon Claw? You do. Dope. And hang on. What's the next one? Quicksilver, that's a real thing. A Vampire Fang. You do have a Vampire Fang. Okay, cool. Now, the last thing that we have to check is to make sure that the fantasy ingredients that we just put in does not constitute any required pairs. And where did I have that? It was around here somewhere. ARPP. RPT. ARPP. Oh yeah, here it was. Yeah, so there's this, and then for each one, can I just do nested indexing here? Does that work? Nope. Fair enough. for each one. Result index of omega. It's not results, it's ingredients. And just mix these. It's perfectly fine. Okay, so these are required pairs. We added Troll Blood, Demon Claw, and Vampire Fang. Oh, yeah, these are a required pair. So we want to take out one of those. Troll Blood, Demon Claw, Vampire Fang. Angel Feather? You don't have. Giant's Toe? You do have. Now, if we take Giant's Toe, does that consist of some? By the way, this would be a lot easier if I just like, so ingredients index of bark skin potion, and it's not ingredients, it's results. Yeah. Begin close. So 13 index of, what was it? RSAC, like this. Right, okay, cool. And where was I? So Giant's Toe is the question. Giant's Toe pairs with Redwood Sap, which we will never, which we'd never add because it's just like Redwood Sap is a real item, so it doesn't increase our fantasy ingredient score. Troll Blood, Demon Claw, Giant's Toe. Okay. Yeah. All right. So these are ingredients that our buddy has. It has the required ingredients for Barkskin Potion. It gets our fantasy ingredient score up high enough so that we don't hit magical explosion or inert glop. And I don't exactly know how mutagenic ooze works, but it seems to have some correlation with like other required pairs other than like the potion you're trying to make, right? And our minimum and maximum number of ingredients for Barkskin Potion was 4 and 8, so 5 puts us solidly in that range. I'm going to say ship it. Yeah, this video is getting pretty long already. Let's just ship this guess. So Crushed Onyx, Ground Bone, Troll Blood, Demon's Claw, Giant's Toe. And these are, let me just double check that these are actually ingredients that he has. Demon Claw, Giant's Toe. What was the other one? Troll Blood. Yeah. Okay, cool. All right. So there's an answer thing posted here, which I'm going to click on. So I'm going to give you like 5 seconds to pause the video or leave or whatever if you don't want to be spoiled. Okay, although you're already like, I guess you're already pretty spoiled at this point. But hey, click away, all right, if you don't want to see it. Last chance. Okay, here we go. Rule sets. Magical potency. Oh, yeah. Dope. Okay, awesome. Yeah, we noticed this. So we noticed this by sorting the percentage of each ingredient for each result. And then like magical explosion, all the magical stuff occurred at a higher percentage than all the not magical stuff. Right? And then for inert glop, it's the other way around. Yep. Yeah. Yeah, we figured this out. Okay. Direction. Bark skin. Crushed onyx ground bone. Got it. Bonus objective. For bark skin and necromantic power potion. Some ingredients aren't key ingredients for any potion. Angel Feather and Fairy Tears are useful because they raise your fantasy score. Crushed Sapphire and Quicksilver have no effects ever, and you shouldn't include them. Okay, cool. Oh, okay. Got it. So, like, our intuition about mutagenic ooze was correct, but it's not deterministic at 2 or more. It's some probabilistic thing. So that explains why, like, basically the required pairs, each one of them was used in mutagenic ooze at least one time, but I was confused about why, like, if that was the rule where it's just like, okay, you include 2 or more you include required ingredients for 2 or more potions, and you just get mutagenic ooze. I didn't think about like whether it would be probabilistic, so that makes sense. But okay, we sort of got the gist of this, I think. Yeah, okay, that all makes sense. For best success, crushed onyx and ground bone. Not include key ingredients of any other potion, and include exactly 3 magical ingredients. Troll blood and vampire fang. Include crushed onyx and ground bone. Include demon claw and giant's toe, which I'm pretty sure we did. Yup. Include 1 of troll blood and vampire fang. Nice. You don't include these. Okay, so I think we did it, right? So we have the required ingredients. We're up to 3 fantasy ingredient score. None of these are required ingredients for anything else. Plus the old mage actually has all of these ingredients. Dope. What's the bonus objective? Crushed onyx and ground bone, necromantic power potion, beech bark and oaken twigs. Okay, yeah, so you switch them around. Yeah, okay, that's cool, I guess. Oh, and you generated a data set. Okay, cool, I guess. Oh, yeah, one thing I should have checked, there's some probabilistic stuff in this evaluation, right? So it would have been cool to like look at whether there were duplicate results in the data set. And then for things that are duplicated, see what percentage. That's what I should have done. Uh, yeah, and I actually kind of knew this. So when we looked at the fantasy ingredient thing, and we saw that like if you include, what was it, 3 or 5, you get 50% of some failures. So I already kind of knew that part of this was like the whole thing wasn't deterministic, right? Like part of this was probabilistic, so I should have checked that. Oh well. Blah, blah, blah. Okay, cool. Well, anyway, that's Data Science Challenge for D&D Sci. I will put links to this and to the index in the video description. Let's see, what can we say overall about this? First of all, leave a comment if you enjoyed it, and if you want me to do more of these problems, I might do them. We'll see. But I think that I think there's some stuff in here that would be probably easier to do in Excel or some spreadsheet, honestly. But having worked with large data sets in Excel, it's pretty much a miserable experience. Thing just chugs along, especially for like a lot of the outer product stuff that we were doing. Whereas APL is super performant with this. Plus, I mean, it helps that the data set was formatted as a Boolean matrix, which is APL's bread and butter. But everything was very snappy. Really, the limitation was just me trying to figure out how to state the different analyses that I wanted to do. And if we look at all the stuff that we, came up with here, this is, what even was this? FICR. I didn't even define it, so that's cool. This was, oh yeah, the fantasy ingredient calculation thing. Yeah, that was with like a nested key and yeah, interesting. So that one's pretty long, but everything else actually isn't too bad, I don't think. A lot of outer products. There's probably more efficient ways to do a lot of this, but doesn't matter. The performance is good enough where I don't have to worry about it too much. So, I mean, I would say it's a halfway decent sort of data exploration tool, right? Anyway, yeah, leave comments. Let me know what you think. And otherwise, I will see you next time.